First of all, I would like to thank organizers for creating this amazing community lunch series and for inviting me to share my story. And also thank you to all of you for coming here to hear more about my path to Michigan. So I'll briefly introduce myself. So I'm Anchal Sareen. If you find it hard to pronounce my first name, you can call me Sareen. And I'm an assistant professor in this department. And if you haven't seen me before, that's not your fault. I just joined last month. So I started my journey here on January 3rd. So it's been just a month. And in terms of research, I am a fluid dynamicist, and I specialize in experimental fluid mechanics. And before coming to Michigan, I had diverse research experience from 4 different continents. And I worked on several research areas like flow structure interaction, bio-inspired drag reduction, multi-phase flow, etc. And currently, I'm also an instructor for Fluid Mechanics Course 1 in Mechanical Engineering. And from following fall semester, this course will be cross-listed between NAMI and ME. So watch out for Fluid Mechanics session by me. So I'll start with beginning of my journey. So I was born and raised in India, and I come from a city called Chandigarh. It's also called the City Beautiful, and it's known for its architectural design and urban design, and some of the few glimpses of where I grew up. And when I was growing up, everyone would ask me this question: what do you want to become when you grow up, right? So I was, of course, thinking about it throughout my journey. And it's very interesting to see how what I wanted to become changed with time. So in my first and second grade, I wanted to become a teacher because that's what I saw. And I was very fascinated by teachers, the passion they bring into their class, educating the next generation. And then I started getting interested in science. And then I thought, I want to become a scientist. So that's like 4th to 5th grade. And then my father would try to influence me and then talk about Indian administrative services and would say, you would have a lot of power. You can really change and create an impact. And I would be like, oh, I was getting influenced. So I decided, okay, I want to become IAS officer. So that's 5th, 6th grade. And then I think he was not very successful. Teachers won again. And then a lot of times in my schooling, teachers would say, we really need cure for cancer. And I got intrigued again. I want to become a scientist and a specific scientist who would cure cancer. And then I was like, maybe a doctor. So all these things, they were happening until 8th grade. And then I was fascinated, just like any other kid, by the prospect of becoming an astronaut. I felt like this is the biggest adventure you can have in your own life. And wow, what a fascinating job. And then right about that time, we had Columbia crash, and there was Indian-American astronaut Kalpana Chawla, and she became my childhood hero. And since then, I decided I want to become an astronaut. And that ambition stayed with me until my undergraduate. So when I was finishing my high school and I was looking into undergraduate, we have this entrance exam nationwide, and I wanted to pursue aerospace engineering, and I didn't get that. The second option was chemical engineering because my brother was a chemical engineer. So undergraduate, I went to south of India, and I did my undergraduate degree in chemical engineering. And I started loving fluid mechanics. I didn't like chemical engineering at all. So during my undergrad, we had an opportunity to go for undergraduate research internship. So I decided to go to France in École Polytechnique. And when I went there, I was mesmerized by fascinating research being done in fluid mechanics. And they had a very specialized master's program in fluid mechanics. And that's when, after my undergraduate degree, I decided to go to École Polytechnique in Palaiseau and pursued my master's degree. So that was my first experience with research. And Oh my God, it was tough because I was coming from chemical engineering background and I was admitted directly to the second year of master's with fellowship. I was very excited about it, but it was a big change for me. But I got hooked with fluid mechanics and I decided I want to do a PhD. So that time I was looking into my options. I applied everywhere. So I applied in the US, 4 places, and also in Australia. I got some offers from the US, but in Australia, they had a very nice funding model. So you can get full fellowship for 4 years, no tuition fees, living expenses. And I was like, wow, let's go there. So I went, before I went to PhD, I had a gap of 9 months. And during 9 months, I became a research assistant in Indian Institute of Science. And then I explored within experimental fluid mechanics, another research area. And I was involved there in research. And then I moved to Australia. And I went to Monash University in Australia, where I started working on flow-induced vibrations and how we can suppress them, because it's a big issue for marine engineering, right? So when I was there, my dream of becoming an astronaut was not there anymore. So that was my childhood dream. So I wanted to become a scientist, but I was not sure what exactly do I want to become, right? In what setting do I want to work on, right? So I decided I want to do a postdoc. And as you can see the trend here, I decided I want to move out of this continent. And I came to the US. So I came to aerospace engineering now. So you saw I started with chemical engineering. My master's was in fluid mechanics. My PhD was in mechanical engineering. In my postdoc, I was in aerospace engineering department. And I was at University of Minnesota for 3 years. And then after I've had this multidisciplinary and multi-continental research experience, again, I was stuck with question, what do I want to do now, right? I want to be a scientist. So that was not changing anymore. And then I decided about my next step. What's next, right? I can be a scientist in a national lab. I can join an industry, R&D team, or I can become a faculty, right? Where do I want to go as a scientist? Some people are calling this as midlife crisis, but I don't think it was midlife crisis. So finding my purpose, because this is for all the students in NAMI, I decided I will highlight how I figured out what I want to become and found my purpose. So it may help you find your own purpose as well. So I thought it's worth sharing. So have you seen this Venn diagram before? Finding your purpose? If not, it's very, very helpful. So for finding your purpose, all you really have to do is find an intersection of all these things. And I was evaluating all these things during my postdoc, during COVID time. So what am I good at, right? So I was having, so it requires some level of self-awareness, right? What are your strengths? What are your weaknesses? What kind of things give you good feedback, right? So I was deciding I'm good at, I felt like science communication is something that I'm good at, and I like doing science. What do you love? So I loved teaching and interacting with students, but I never wanted that as a full-fledged career. So I never wanted to be a high school teacher, let's say, but teaching was one of my passions. So I loved teaching. And then what can you be paid for was something that comes in the end. And the most important thing is what the world needs, right? And especially for finding your purpose, I feel like the motivation that I get is what application, what benefit, or what impact I'm creating through my work, right? So all this time, I've been working on fundamental science. So in academia, most of the focus is on fundamental science. I liked research, I liked science, but I was not seeing that impact that I wanted. The motivation that will make me get up in the morning and go for the lab, that this is something creating impact. When I talk to people about my research, I want to get excited and motivated. So I was really looking for this. So I felt like this was the missing piece. And all this time I was working on someone else's idea. I was working in their lab, right? And turning their vision into reality. what is my vision, right? What kind of research do I want to do? So I took around 3 months. Again, we had a lot of time during COVID. So I took 3 months and figured out an intersection, and I decided it's the faculty job. So I like teaching, but I never wanted it as my full-fledged, the only thing that I'm doing. So faculty, as a faculty, you have to teach, right, at Arvin, and I like teaching. And then there's a lot of science communication involved, right? So when I'm teaching this science communication, when I go for conferences, present my work at several places, that's science communication. When you're pitching grants to all the federal agencies, you're communicating your science, right? So there's a lot of science communication involved. And there are so many routes of impact. It's not just the kind of research that I'm doing that's benefiting the society, but there's an impact that you create by influencing your students, right? If in my class, even if one person gets influenced and does something to change the world, that's enough for me, right? So there's a route of impact through my research, through my teaching, through my mentoring, right? And through my science communication. So I felt like this is like really, really influencing an impactful position, and has different elements that I liked individually, right? And then I decided I want to become a faculty. And the most important thing was I wanted to become an independent researcher so that I can choose my own research direction, right? So that was good. I figured it out, and I'm sure you all will figure it out eventually if you haven't already. And this is something which is very helpful. So that's why I thought I will share it with you. So I wanted to become a faculty. The next question was, if I become an independent researcher, what kind of research would I like to do, right? Finding my research vision. So that also took a lot of brainstorming, right? So I asked myself these two questions. As an independent researcher, what would I like to work on? Right. So I've had a lot of experience in experiments in fluids from several different labs in 4 continents. And I worked on very different areas as well. And I changed my area from PhD to postdoc drastically as well. So my question to myself was, okay, if I become an independent researcher, what should be my research vision, right? And how can I combine all my prior research experience into a common research theme? Right. So I was going through this and brainstorming, and it was already past a month or so since I decided I wanted to become a faculty. So remember, all this thing was happening during my postdoc. So that's exactly when things were starting to change for me. So in the summer of 2019, when I moved to the US, Australia was going through one of their worst disasters ever. Right? And it was with unprecedented intensity, size, and duration bushfire. 84 million acre land got burned and 8 million animals were killed, right? And then we were all stuck with COVID, right? So since I came to the US 6 months afterwards, we had COVID. And that was a stark reminder of fragility of life that we always take for granted, right? So everything was stopped. I was working from home. And then I saw the sequence of events. So we were all watching news, right? Following news during COVID. And I saw there's increasing wildfire in California. And then there was tornado in Oklahoma. And then Hurricane Michael and drought. So one thing was clear. All these events are becoming more extreme, severe, and more frequent, right? And in United Nations Climate Report 2021, they also sounded code red for humanity. And this was all happening while I was also thinking, what kind of research would I pursue, right? So then I asked myself question, how can I leverage my research experience and help solve some of the most pressing energy or environment related issue, right? So I'm a fluid dynamicist. How can I use my expertise, even if I contribute a little bit, even if I do fundamental science, but if I'm contributing a little bit, that's enough for me. So that's when the vision for my future lab was born. And that vision became combating the climate change, right? And I realized that all this time, all the research that I've done can be broadly classified into two areas: fluid structure interaction and multi-phase flow. So now I was thinking, how can I leverage these two areas to solve some of the most pressing energy environmental related issue? So I came up with my plan, first 5-year plan. So I said in fluid structure interaction, I would have lab experiments and also field measurements, and I would work towards developing and optimizing novel methods of renewable energy harvesting, and then energy efficient ship propulsion, and bio-inspired strategies to reduce drag or enhance lift, overall to improve hydrodynamic performances of hydropropulsors. And along the multi-phase flow side, I thought we would do tabletop experiments, very easy to set up my lab. And I would work on fundamental projects, again, that will help us solve some of the environmental issues, like how can we optimize carbon dioxide sequestration process, right? And mitigating plastic waste in oceans. So that was it. That was my vision, which I was looking for. And once I realized this vision, I just went for it. So I applied for several places, and I was very, very lucky that I got an offer here. And our chair is right here. So he, along with everyone else, voted, and I was hired. So I feel very lucky. So now I will give a brief overview of the projects that I have in my lab. So this was another thing. So in 2021, August 2021, I saw an article. So if you're looking for something, right, the universe will give you signals. So this is one of the signals I like to call. So I read an article on The Guardian, and it was 2021, very recent. And the title was Game Changer Emerging Wind Energy Technology at Intermediate Scale. And then this was the prototype of a wind turbine that is bladeless, and it was prototype given by a Spanish startup company, Vortex bladeless. And they touted this as game changer because it can bring wind energy technology to your home. Because with the wind turbines, the technology is already mature, right? But you cannot bring it at the utility scale of a single house because they're huge, right? They create a lot of noise, right? And they're not good for birds. And they said that this bladeless wind turbines can actually fill the gap because it has low current flow velocities. You can put it at the scale of single household along the highways, and they're harmless to birds, generates no noise whatsoever, very low maintenance cost, and can be placed very close together, unlike wind turbines that have to be placed very farther apart. And that is something that is very related to what I did in my PhD, but I never realized its importance. So what it actually works on is a thing called Vortex Induced vibration. How many of you know about Vortex Induced vibration? I will be teaching in Fall Fluid Mechanics 1, so you would know. So whenever we have any body, let's say a cylinder, and then we have flow from left to right, we have these alternate vortices that are shed past that body. And that creates fluctuations in pressure on the body. And if you allow this body to move freely along the transverse direction, then it does these vibrations as you're seeing. This is a CFD result that I got from a reference. And you can use that to convert to electrical energy. And that's what Vortex Tacoma did. But this technology is still in its infancy. As you can see, for 2.75 meter cylinder length, it's generating just 100 watts, right? It's just a bulb, right? And that's because this technology is not mature, just like wind turbine technology. It's still in its infancy, and there's a lot of room for making this optimized, right? For example, the shape of a cylinder, as it turned out, is not a great shape for extracting renewable energy because these vibrations, they happen for a very narrow range of flow velocities. There are gaps between several branches of vortex-induced vibration response. So there are a lot of challenges right now. So one of the idea of my research group would be, how can we optimize these fluid structure interaction system for maximizing the energy output? And Enercon, again, we are from Navy. Anyone of you have seen this Enercon? Nobody? Okay, so it's a cargo ship. It's still in operation. And it's owned by Germany company Enercon. And what they have is, these are rotating cylinders. And whenever any body rotates, so you might know this from sports, so curveball, right? And banana kick. So whenever you give rotation to a sphere or a ball, it changes its trajectory dramatically, right? That's the curveball. And that's Magnus effect. So in Magnus effect, if you rotate a body, what it really does is it deflects the wake of the body towards one direction, and there is equal and opposite force on the other direction, which is Magnus effect, and that's what leads to curveball. And the idea was, can we use that Magnus effect for propulsion? So this ship uses Magnus effect for auxiliary propulsion. So it's not still at that stage where we can use this as full-fledged propulsion device. So the idea here is, can we employ active or bio-inspired passive methods to optimize Magnus effect as propulsion mechanism for ships, especially because ships use bunker fuels, which is the worst fuel ever, with so much of carbon emissions, and we really need to bring it down. And especially in Navy, I think this is what we must do in the next 5 years or so. So I also have a sure summer undergraduate research project on this. So if any one of you is interested, you can contact me after this seminar. And then nature has its own fascinating ways, right? So nature has evolved over billions of years. And then we have these shark scales, which manipulate the flow around the shark to reduce drag and increase maneuverability, right? So the idea here is, can we take inspiration from nature and use that to make our propulsors more efficient, let's say, right? Or can we use these strategies in our ships to reduce the fuel consumption? Or for any propulsor for that matter, can we use these bio-inspired strategies to improve the hydrodynamic performance? So that's also one of the projects in my group. And along the side of multi-phase flow, we have fundamental tabletop experiments. The first idea is, if you really want, in next 10 years, if we want to reduce the emissions of carbon such that we don't exceed the 1.5 Celsius degree rise in the pre-industrial levels, not only do we have to reduce the carbon emissions and switch to renewable energy as soon as possible, we need to actively remove carbon dioxide from atmosphere and store it long-term in saline aquifers, for example. So that's industrially viable option, and people are already using it. So idea here is, in porous media, whenever we have any fluid going, then because of surface tension, it gets trapped. And that's how the oil gets trapped in porous media, and we extract the oil, right? And oil refineries, they always take measures so that they can extract as much oil as possible. Right? The same technology now we can use to store carbon dioxide long-term, right? One of the ideas is, can we use the already depleted oil reservoirs for storing CO2 long-term? So here, the project is very fundamental in nature, idealized model of porous media, and looking at how does a fluid get trapped, right? What are the various characteristic parameters that leads to this trapping of a fluid? So this is a very fundamental project, but with very large implications. And another project that we have right now is, how does the settling process of various particles is affected when we change the texture of that particle moving through fluid-fluid interfaces? It's again a very fundamental tabletop experiment that my lab is beginning to set up within a few weeks. And we're looking at characteristic parameters like surface roughness and surface variability and inertia. And again, very small scale and fundamental project with big implications, as it can help us reduce plastic waste in our oceans. So that's the overview of my new lab, Experimental Fluid Dynamics Lab, which will be based in marine hydrodynamics laboratories at the central campus. And you're welcome to check out the website, and we are growing. And I invite you to come and join us, and we are building our team. And with that, I would end my path to Michigan. I hope you have some takeaways which help you realize your purpose in your life. So with that, I thank you all of you for your attention. So now we can have an open floor for informal conversation, if you like.
On the previous slide, what were you measuring with the green dye?
Oh, yeah. So this is dye visualization. So on the left, we are looking at a sphere, which is mounted rigidly in the water channel. And we have a fluorescent dye. So you're looking at streak lines. So if you release dye here, then using ultraviolet, you can visualize the dye and then look at the structure. So it's, as you can see, it's highly three-dimensional turbulent structure. But for the case of cylinder, it's very elegant vortex shedding like we saw in the CFD result before. So again, I have an open, pure project in the summer. I'm looking for an undergraduate to join and work on energy efficient ship propulsion projects. So any of you interested, feel free to contact me. Yes.
What was the biggest difference you saw at the schools in different countries?
Oh, yeah, that's a very good question. Yeah. So Europe and Australia, I would say, was very similar. So people would, in terms of work culture, people would work only from 9 to 5. In France, the entire August was holidays. and I was surprised because they were doing very, very good science, right? A lot of good publications and good research, but they were very, very productive, right? 9 to 5, and you won't see anyone during the weekends. And same was the case in Australia as well. So I think they have a very nice work-life balance. So when I came to the US, it was very, very different. So, so over the weekends, I would see all my colleagues in the lab, and I was like, okay, I don't work on the weekends. I will go for a hike. And they were like, so that's a very different, but I feel like there's a Parkinson law. So if you allow yourself, let's say you have to do a homework for your classes, and if you allow yourself to take the entire day, you will end up taking the entire day. But if you restrict yourself that, no, I'm going to give myself 3 hours based on your previous experience, you know, you would take around 3 hours, then you would finish it in 3 hours. So working long hours, I don't think translates to more productivity. Maybe you become less productive if you have a lot of time, right? So that was the work culture difference between Europe, Australia, and the US. That's what I observed. Yes.
I mean, looking back, when just kind of thinking about your slide, talking about kind of your dream job at different ages. When you look back at those, was there some sort of common thread that you would say you've continued on now?
Yeah.
And like, how did you kind of discern that?
Yeah. So it's like connecting dots backwards. You cannot connect them forward, right? Steve Jobs said that. I didn't. So when I look back, in the beginning, I didn't know that. But when I look back, I could see that in the beginning, I was interested in teaching. And I always loved teaching. And I would always take that opportunity to teach, and science. So teaching and science is the common theme you would see during all age, all the grades, that you would see that I wanted to become a scientist, maybe astronaut. So there's some sort of science or research involved, and teaching or science communication. So that's the common thread, I think, that was. So I was building skill unintentionally. The skill was being built from my childhood until this stage. And I thought it would be important to share that, because so many of my friends, they would say, oh, right from the childhood, I knew I want to become a basketball player, right? It never happens all the time. I used to feel very pressurized to find my passion, because wherever you go, even if you watch like motivational videos on YouTube, which I know most of you would watch, they would say the secret to success, find what you're passionate about, right? And so I used to feel very pressured. What's my passion? Right? I never found it. So, and I realized it's very common. Like, it's not necessary that right from the beginning of your childhood, you would know exactly this is what you're meant for, this is your purpose. And then now you're, just like Serena Williams. Very few people have that. So you have to just be self-aware and realize, what are you good at? That Venn diagram again. Like, what are you good at? What kind of things you like doing? How can you help the society? And can you get paid for it? And you may see that there are several things you could do. And you may try different things and figure out your purpose that way as well. Yes.
I guess this is kind of like a strange question, but like, if the opportunity to become an astronaut,
Yeah.
something you would consider, you completely grab that idea and what to do.
I have asked that question to myself. So right now, if you have $1 million, you can become a space tourist, right? SpaceX, Blue Origin, you can be a space tourist. So if I ever become a millionaire, which is highly unlikely as a faculty though, but I would take that opportunity to go outer space, because I still feel that it's a great opportunity. But so as you might know, like NSF, they have a funding program. So if you have come up with some projects where you would like to do it, an international space station in the absence of gravity, you can pitch that idea to them. And then probably they'll ask the PI, the postdoc or student, to go in space, things like that. So I've considered that. So right now I'm very focused on establishing my research agenda and solving some problems. But down the line, I think when I get old, I would like to take that opportunity and become a space tourist one day.
Have any ideas with the penguin? I saw the picture of the penguin on the slide.
Yeah, idea about penguins, like
Like what they could inspire that like maybe a shark wouldn't.
oh yeah, so with penguins, what they have is their skin, they have very micro bubbles. So they release micro bubbles very, very close to their body. So that's something people have already getting inspired from, for example, in Emmy and also NAMI Professor Sessio. So he has done a decade-long work on microbubble drag reduction, where they have turbulent boundary layer and they inject microbubbles to reduce drag. And Professor Dowling would be able to comment on that, so it has been implemented on ships as well, but I don't think it's has become a mainstream drag reduction technique yet. There are a lot of challenges with that, but that's an idea which came from penguins. So as an independent researcher, like if you come to do a PhD, you unleash your creativity. If you come up with an idea, let's say watching birds, some of you may be bird watchers, right? And you may be watching birds from your childhood and written down notes on different types of tail configurations or wing configuration. And then let's say you come up with an idea, why do birds use this morphology? Why do they fold their wings when they're plunging down, etc.? So all those creative ideas you can bring, and then we can turn that idea into reality in our lab. So you'll have that kind of creative freedom. Just an invitation. Any other questions?
Yeah, regarding the research that you have in mind for the offshore wind, for the wind renewable energy, is there any application for that to be extended for the offshore wind as well?
Yeah, so why we took wind turbines to offshore, because we want high winds, right?
Yeah.
And we have them like 100 meter stall, 80 meter stall, just because close to ground, we don't have enough wind speed for wind turbines. For if you have a converter which is based on flow-induced vibrations, they don't need that high speed. So they are meant for low speed. So, I mean, we don't need to go offshore for that matter. For wind turbines, it makes sense because offshore you have very, very good wind speeds. But these can, of course, be used for marine renewable energy. And in our department, Professor Benitez has already demonstrated that. And they have their converters installed in St. Clair River. So, which is extracting marine renewable energy from river currents. So, of course, it's flow-induced vibration. You can put it in the wind, make it wind turbine, or you could put it in the ocean or river currents to extract hydrokinetic energy of fluid. What happens now?
We say thank you very much.
Okay.